All right, let's move on to a whole new type of bonding, covalent bonding. Can you figure out what it's doing? Break down the word. Co, meaning like a partner. Valent, that looks an awful lot like valence shell. Bonding. So let's take a look. And yes, if you didn't figure it out from my hints before, covalent bonding is when they share or cohabitate basically in the valence shell of two different atoms. What does this occur between? Two nonmetals. So remember, a metal and a nonmetal, the metal would give up an electron and it would be taken by the nonmetal. Nonmetals both want an electron, so they're not going to give one up, but it turns out they will share one. And so that sharing is where we get the co, like it's cohabitating in that valence shell, that's where we get valent, to create a bond between the two atoms. So notice that we still follow the octet rule. That octet rule, meaning that they want a complete valence shell, usually with 8 in it, that's where we get that oct. But in this one, this is hydrogen and this is fluorine. Hydrogen only has one shell that can only hold 2, so it needs one more. Fluorine has 7 and it wants one more to get 8, thus the oct. And what they do is they share one of each. When you share one of each, then you can say, oh look, this hydrogen has 2 electrons in that valence shell. And you can say this fluorine has 8 in its valence shell. See, 1, 2, 3, 4, 5, 6, 7, 8. And it's basically how that works out. But it doesn't always work out so perfectly. Sometimes you need more of them, just like you do with the ionic bonding, in order to even out the numbers. So notice we have phosphorus here, and then we have chlorine. Well, phosphorus actually needs 3 electrons, but chlorine only needs 1. Chlorine's only going to share 1 electron at a time because it only needs 1 shared with it. So that means it will take 3 of these chlorines to bond with phosphorus like that. So it ends up creating something like this. Also, notice our Lewis dot diagrams and how useful it is. Notice this is why I also wanted you to put 1 in each before you paired them, because it gives you a good idea of where they're going to bond with each of them, right? Luckily, we can still use that cross-oxidation method. We can use that because it still tells us basically the need that they have, right? We just have to reduce it a little bit more. So if I'm looking at carbon here, we say carbon needs 4, oxygen needs 2. So if I rewrite these, carbon and oxygen, I'm going to make that 2 down there, that 4 right there, just cross oxidation. Then I'm going to reduce. I'm going to get 1 carbon to 2 oxygen. Oh, and look at there, carbon dioxide. I think you're familiar with that, right? So then let's look at sulfur. Sulfur, we said, had a -2. Fluorine has a -1. So we're going to get 1 with that, 2 with that. That's just crossing over. We don't need a 1. That becomes redundant. And so we have it just like that. And then, let's see, carbon, we already stated it was a 4. And chlorine is a -1. And so we can see where it's going to cross over. You get 1 and 4. Drop that 1, and you're going to get CCl4. And that's how you do them. And I didn't write up here, that's plus, that's minus. Yes, carbon we're saying is +4, but remember carbon is a nonmetal, and so it really needs 4. It's at the halfway point. So it's going to want to go positive or negative. That's why it still works in this way, because it's just as easy to lose as it is to gain. So we say it's +4, but really it can be a -4 for this case. Now, we've already seen that covalent bonds are different from ionic bonds by the fact that they're not creating ions. We've also seen that they share electrons, even though we can still use that cross-oxidation method, and we still are looking for an octet rule. But Covalent bonds also share some unique things that you can't do with a ionic bond because they can share more than one if they have more than one to share. And that's where you get multiple bonds. So take a look at like nitrogen that we have here. So nitrogen has 3 open electrons. It needs 3 in order to complete its octet, right? Well, that means it can bond with another nitrogen, and it can create a double bond or a triple bond. And so if it bonds together in that way, then it's just going to share multiples between just 2 of those, and that way they still end up full up. Because if you look down here, look, this steel, if you count all the ones that it's sharing plus the ones that it has free, will give you 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. But we write it a little bit differently. When we write it like that, we tend to write 3 straight lines. A lot of times if you're drawing and you're notating in the Lewis dot model, a shared bond, a shared electron. So let's just say a shared one between, what do we say? Let's say oxygen and chlorine. So here's oxygen. Oxygen has 2 here, and we're going to do 1 here. And then chlorine. Chlorine has pairs there and 1 there. And so you would draw it just like this. But really, instead of showing that line, or those 2 dots, you draw a straight line showing they're sharing those 2. So a line counts as 2 different electrons when you're drawing the Lewis dot that way.